Good morning, good afternoon, good evening, depending upon where you're joining us from. I'm Ira Feldman. I'm the Executive Director of MEPTEC, and I would like to welcome you to today's Semiconductor Industry Speaker Series presentation hosted by MEPTEC and IMAPS. In the speaker series, we have twice a month presentations. We are working to finalize the presenters for April 7th and April 21st. As soon as they are finalized, we will let you know, but our plan is to have a presentation next week at the same time, 11:30 a.m. Pacific time. If you're interested in speaking at a future webinar, please contact myself, ira@meptec.org, or Dave Town at IMAPS. So we look forward to suggestions on topics and presenters. In terms of MEPTEC, our next event will be an online event that April 28th and 29th, discussing supply chain security, especially as we have more and more electronics in our devices and more advanced packages. There are more opportunities for issues. So we will be talking about the challenges of making sure that there is a secure supply chain. You can find information and free registration courtesy of our sponsors at events.meptec.org. Just go to the MEPTEC website. In terms of MEPTEC, MEPTEC is a membership and sponsorship supported organization. If you haven't joined or renewed, please do so at meptec.org. If your company is interested in sponsoring, please reach out to us. Your membership and sponsorship enables us to do free events like this and to publish the MEPTEC report. And certainly we look forward to any feedback you might have about MEPTEC and our programming. So today on our Semiconductor Industry Speaker Series presentation, we have Tom Green of TJ Green Associates talking about MIL-SPEC hermeticity testing of Class 3 medical implants. It's my pleasure to introduce Tom Green. He has over 40 years of combined experience in industry and academia and the Department of Defense. He is a recognized expert in hermetic testing and moisture-related failures in medical and military products. He consults on next-generation medical implants, which he'll talk about in his presentation, and organizes the yearly Middlebrook meetings where they talk about moisture-related failures and hermeticity. He also has a deep experience in related issues in testing wire bond die attach failure analysis. And his organization, TJ Green Associates, organizes the CMSE Components, Military and Space Electronics event. They will be virtual this year in about 3 weeks, and he'll talk about that briefly at the end. And he's also involved in IMAPS as a fellow. So it is my great pleasure to turn the floor over to Tom.
Thank you. As Ira mentioned, my name's Tom Green, broadcasting live from Bethlehem, Pennsylvania. And for the next half hour or so, we're going to talk about Class 3 medical implants and hermeticity testing. And we'll take questions as we go. I want to start by giving a special thanks to MEPTEC and Ira for putting on these speaker series. I've been involved in a few, and it's great to see them working with IMAPS. Those are two great organizations, and we're lucky to have somebody out there doing it, so we get a chance to share information and stay in tune as best we can while we still endure the lockdown and the pandemic. So, all right, so today I'm going to briefly go over some of the test methods in MIL-STD-883 regarding hermeticity. So the big ones, test method 1014, that spells out all the procedures and methods for determining whether or not you got a good hermetic seal. But that test method is closely related to another one, test method 1018, for residual gas analysis. Now, many years ago, the medical device community adopted these standards, and there's some issues, there's some things to be aware of when you try to apply these test methods to a medical implant. For starters, the operational environment's not quite the same. Instead of minus 55 to 125 C, you're working at basically, 37 C body temperature. And device lifetimes, things of that are a little different. So I'm going to touch on some of those pitfalls. And then towards the end of the talk, I'll walk you through how you can make a projection of how much moisture you would expect in the device for a given leak rate and a given starting residual gas moisture level at time 0. So we'll get into all that in a minute. But you can see here, our focus is class 3 products. So a class 3 device is one whereby if it were to fail, could put the patient at risk. Ones most people are familiar with are pacemakers, cochlear implants, neurostimulators, very common. And even to this day, a lot of them are hermetically sealed in titanium cans, even though there's a lot of work and interest in developing non-hermetic implanted products, just as they're in the MIL community looking at non-hermetic solutions. So one of the things you'll notice about some of these devices is they all have a molded or plastic header encasing the hermetic feed throughs. So that's something that can be a problem if you're gonna do leak tests. And many of them contain a silastic overcoat, which is also a little bit problematic when you try to employ a conventional leak test methodology. So, but these are the kind of devices I have in mind. Now, dating back to the early 70s and into the 80s, in some ways, the devices haven't changed all that much. Cordis was a leader, but even back then, they had some kind of molded epoxy header over the hermetic feed-throughs. But from the very early days, the medical device community really borrowed from the military qualification and specification system. So to this day, MEPTEC is called out or used in some variation or some form or another. And because back 70s and 80s, the only real group was the DoD, the Department of Defense, with NASA and with keeping up with the Russians and those kind of things. There's a lot of money poured into military specs. When I was in the Air Force, I worked at a place in upstate New York called Rome Air Development Center. They were the ones that were responsible for these test methods. Okay, so just to start off, what is hermeticity? To the layman, it's just maybe an airtight seal. To somebody in this business, especially if you're immersed the way I am, to me, it's hermetic if it passes test method 1014. For a given spec or air leak rate, there's a variety of methods in that test method that can evaluate a hermetic seal. Now, the other important thing to think about, MIL-STD-883 was written for devices, hermetic components only, that were made from glasses, metals, or ceramics. So if you create a cavity, a hermetic cavity, made from any one of those materials, you can disregard any moisture permeating through the bulk. And so really helium leak test is about, detecting fractures or cracks or crevices in the glass to metal hermetic feed-throughs, in the weld, or in the braze joint. But once you add an epoxy to that, or suppose you just took a hermetic package and epoxied a lid on it, more than likely you'll pass the test method. But now that's, if you have epoxies in the leak path, then 883 test methods are not the right test to employ. That's a whole nother problem. That's about moisture diffusing through a polymer, and that's a different approach altogether. That's what we call non-hermetic parts. But in a medical device, you got a little bit of both once it's implanted in the body. You have a seal that you hope is hermetic, and then you do some subsequent processing and you hope that subsequent molding of the header doesn't compromise the seal. And then you put it in the body. But if you had a leaker and you just had the molding protecting the inside of the component, well, then it's not that long before moisture saturates that header. It's in, along the interface between the molding and the feed-throughs, and voila, you basically, if you had a leaker to start, it's going to fill up with moisture. And, you can ask the question, why do these medical devices even need to be hermetic? Well, if you look back through the literature, one of the biggest issues facing microelectronics is keeping them free of moisture. There's just a ton of papers and problems that have occurred over the years that are really moisture-related failures. So, one of the most susceptible parts, if it's a hybrid, a lot of these implants are basically hybrids. They're chip and wire, bare die, with passive components, maybe a double-sided board. But the bond pads on an aluminum chip, where it's a typical silicon IC, they're very sensitive to moisture. And then if you have any kind of moisture on the surface of an integrated circuit, you could have leakage, you could have surface conduction, you could have electrical issues. There's a whole lot of new MEMS and sensors that are being hermetically packaged for just an explosion of new medical products. And those all have to be protected from outside environments and from moisture. In some cases more than others. So if you're starting out designing a new medical device, one of the things you want to look at is what is the moisture susceptibility of my components in that device. So bare die would probably be a little more susceptible than maybe a packaged device. And certainly any MEMS products have some level of moisture sensitivity. And if it's some kind of a RF device, that there could be problems there. And then dendritic growth, that's basically the result of moisture and ionic contamination and a bias. And you might have to think about how good are my passivations? How well do they protect the chip? So lots of these problems have occurred over the years. This is just an example of one.
So Tom, but is there also in obviously the specs are designed to protect the contents of the package, but are there additional medical specs that address protecting the person the device is implanted in, i.e. like nickel is toxic? So how is there the concept of protecting the patient, or is it assumed that if it's hermetic, then there's no opportunity for poisoning or whatever you want to call it?
Well, that's a great question, because inside any hybrid, any medical device, is just a laundry list of toxic chemicals, nickel being one of them, silver. So I think the assumption's always been, if it's hermetic, you don't have to worry about anything leaching back into the bloodstream. But God forbid you implant something that's got a leaker, you can't out of hand rule that out. But I think everybody kind of relies on this notion of hermeticity. And certainly if you follow to the letter of the law 1014, you got a high probability that it is going to be hermetic. And I kind of relate this almost to, building electronics for space and deep space missions and, military satellites that we want to last 20, 30 years. You have to kind of think about the cost of a failure. And so in medical implants, the cost is harming the patient. And so, yeah, I think those are some really good concerns, but I think that list of toxic chemicals, and there is one at the FDA somewhere, really applies to the outer shell that might be touching the body. And that's why titanium's a great pick for something like that. Okay, now what I'm showing here is just I had to write what's called a GUIDEP report on it, Government Industry Data Exchange. This was back when I was working in Denver. It's an unpassivated nichrome chip resistor, happened to be very sensitive to moisture. And unfortunately, we didn't know about it until it was already built up onto the spacecraft. But silver dendrites is another very common moisture-related failure mechanism. So inside a lot of class 3 implants, they're putting the chips down with silver epoxy. Well, if you have a bias and you have ionics, which you almost always do, then that silver is mobile. It can grow dendrites. So if you want to learn more about that, here's a great IEEE reference. You go on IEEE Explore, learn all about it. Now this is a little different than, say, tin whiskers, a common board level failure mechanism associated with SAC solders. But the FDA, they do a great job kind of tracking any problems. And if you look back through this link, you can kind of see over the past 20, 30, 40 years, there have been more than one moisture-related problem with implanted products. And so usually that comes down to maybe failure to properly test it, or not really understanding the environment. So these two methods go hand in hand. There's hermeticity testing, which really only checks the integrity of the seal. But suppose your glove box was broken and you sealed in a lot of moisture to begin with. Or suppose the polymers inside the device, the epoxies and others, they very easily suck up moisture. And if they start to outgas, you can have high moisture content inside the device, even though it's hermetic, totally hermetic. So our two test methods within MIL standard 883, if you're not familiar with this, that's just a collection of test methods, many of them, 40, 50. The two we're most concerned with is seal, AKA hermeticity, and then it's now called internal gas analysis, but most people still refer to it as residual gas analysis. So one thing you got to keep in mind, anything that was built to 883 is generally intended to work between minus 55 and 125 C. Yet in the body, it's a pretty benign environment. Matter of fact, when somebody says the component must have lost hermeticity, I always find that hard to believe, because these are it's the same technology. They're hardened ceramic or glass to metal match feed throughs. And the body really is relatively benign, but these two test methods are closely tied together when you start to think about how long can I expect my implanted device to last in vivo. So hermeticity testing, it just checks for cracks or holes in the sealing glass. If you weld on a ring frame, a weld joint, fractured glass to metal feed throughs. Those glass feed throughs or ceramic feed throughs, if they get manhandled during manufacturing, could crack, or maybe they come in the door and they're already defective. But what it's not going to test is moisture slowly diffusing through a polymer. So once the part is potted, it's very difficult to do a fine leak check. You can assess a gross leak condition. And when you pull an implant from the human body, if it were to fail, that's difficult to really get a good read on how, if you had a hermetic seal or not. Now, fortunately, when you do residual gas analysis, which I'm going to talk about a little later, by looking at the constituent gases, you can back calculate a theoretical leak rate. So let me just spend a few minutes on hermeticity testing, and then a little bit on RGA, and then we'll do some other things. But when you get a leaker, it could be from the weld, could be from the feed through, or maybe some kind of a raised joint. That's basically what you're looking for. But in an RGA, if you found moisture, the moisture may have been in there at time 0, or it could be high moisture because of a high leak rate. And one thing you got to keep in mind is most epoxies, polyimides in particular, any kind of a circuit board, some implants are just advanced SMT products that are put in there. Well, they all just in room ambient absorb quite a bit of moisture. In some cases, 1% to 2% by weight. And if you do the molar conversion of that inside an enclosed package, a 10 cc package, let's say, that's a huge amount of water vapor that's potentially going to be outgassed, and you have to worry about it. In rare cases, you can have some other things going on that generate moisture. So 1014, I think we're up to notice 17, 1014.17, contains a variety of different test methods. The one most people are familiar with are helium-based methods. And so the traditional method, condition A1, A2, is you do a fine leak first and then the bubble test. And you have to try to force in the tracer gas helium. That's known as a bombing or pressurization cycle. A new method that was just added a few years ago, condition A5, is a high sensitivity leak detector, basically using a mass spectrometer. And there's some real advantages to that. One being you can measure much lower leak rates than would be normally available with conventional leak detectors. There's a radioisotope method, but in the medical community, just because of that word radioactive, doesn't get a lot of attention. We have our bubble test. I love the bubble test. If I have a chance here, maybe I'll show you a video. It tells you where the leak path is. When you fail a hermeticity test, a helium hermeticity test, you don't really know where it's leaking from. But the bubble test, which is for gross leaks, it's like, your bicycle tire that's bubbling. And then there's another methodology, optical leak testing, which has a lot of advantages. There's no helium pressurization cycle. You don't have to bomb it. So that's a big advantage because you don't have to worry about residual heliums and so forth. And finally, there's a cumulative helium methodology that's listed in there. So very briefly, this is how we do leak testing. You either pressurize the part. If you're following with 1014, you pressurize it in helium for some amount of time, put it in the leak detector, and then this is tuned to the, it's a mass spectrometer tuned to the helium field. And it can measure a leak rate after a pressurization cycle. Here's the condition A5, basically a high sensitivity, meaning this instrument could go down and measure leak rates in the 12s, minus 12 range. Let's click along here. Gotta watch my time. Cumulative, that's been around for a while. Used to be Pernica Corporation, now EAG Labs. There's some real advantages to that. And can measure lower leak rates. See, a few years ago, it's gonna be 5 years now, for hybrids that are used in space, they tightened up the hermeticity spec by 2 orders of magnitude. And the industrial base responded by developing some leak testers that can go down to those lower leak rates. Here's the NORCOM optical methodology. This has a lot of advantages, and it's really relying on lid deflection. So in this scenario, you pressurize a part, you look at the surface of the lid, and if the lid bows in like this, then it's sealed. If under an interferometer, it doesn't move at all, then it's a gross leak. And this is really kind of bulletproof for the gross leaks and correlates very well with the other methodologies. There's a lot of techniques to choose from, but the most important, go ahead.
So back on the last one, there was a question, the lid deflection test, they called it laser shearography. Is that, I mean, you're basically looking at the deflection of the surface from true, but
that's correct.
Okay, so I'm not familiar with laser shearography. Does that ring any bells?
What you're looking for, it's kind of color fringing. And by looking at those fringes, you can essentially measure out of plane distortions, down almost in the nanometer range. And so you can relate that deflection to a change in pressure. So the chamber itself is 100% helium, or you could test in air, but you deflect the part and then you kind of look at the rate of relaxation, if there is any. And from that, you can calculate a leak rate. So this technique's been around a long time, very popular in the optoelectronics industry with when you got a pigtail and the fiber attached to your hermetic part. You can't really do conventional leak testing because the acrylate in the fiber absorbs helium, throws everything off. So each one of those methods I described have their strengths and weaknesses, but they're able to make these tighter measurements. So here's the last page at 1014, probably the most important page in that spec and the one that's most grossly misunderstood or kind of misquoted. The information never seems to make it down to the guy running the leak detector, but the spec is given in terms of an air leak rate. And for hybrids intended for space, that's what we call a class K hybrid, the leak rate is 1 × 10⁻⁸ air. We call that L air. That's what you start with when you spec out a part. All right, and this equation, which I want to get to and talk about a little bit, kind of describes how much water you would expect in a device given some ambient condition as a function of time and volume. All right. And the other point I want to make on this slide is the mil specs, believe it or not, people have argued this over the years, are not that tight in a sense. So for most products, if you're actually leaking right at 1 times 10 to the minus 6 for a large package volume, it doesn't take that long for moisture to accumulate in the package. Now, fortunately, based on my experience, when it comes to hermeticity, it's usually all or nothing. You either get a great seal and it's way down in the mud as far as a leak rate, or you have what we call a fine leaker. Now, those are the ones you're worried about, but thankfully they don't occur as often. But when they do, it's a big worry, and that's what you have to worry about when you set your specs. So here's the Hallman equation. We don't have time to get into it in any great detail, but it's really a simple equation. This is what the person would measure at the leak detector. This describes how much moisture, or in this case, helium, accumulates in the package. And that's a term that has to do with the dwell time. So I'm going to jump through this. You can read about it later. If you go to my website, I wrote a white paper a few years back, Practical Guide to 1014. All right. Now, there's some other things to know about the Hallman equation, but normally people would pressurize the part. Now, in the medical device community, they backfill with 25% helium. So you already have your tracer gas in there. But in order to be in full compliance to 1014, you'd still need a pressurization step. And then there's some assumptions in that Hallman equation that, in the real world, is all flow really molecular. The theory and the Hallman assumes a single leak path. Often there are many and tortuous. So I don't want to get too caught up on the theory here, but there are some differences in the theory versus reality for parts leaking into a package. All right, let me get to this slide because this is what I want to get at. Because of that plastic header, it's very difficult after that's put on to measure a leak rate. So in a manufacturing plant, you got to measure your hermeticity right after seal and make sure that any subsequent processing doesn't compromise the integrity of the seal. It's very important. And you just have to be aware of that. And you have to make sure in production you've got the right kind of in-process controls. Now, the other thing that can befuddle you for medical devices is silicones. Just about everybody puts a silastic silicone over the part. Well, if you ever worked around silicones, it's very low vapor pressure and the silicones get everywhere. So if you're doing a silicone process step, anywhere near or after you created the hermetic seal and before leak test, you're liable to block the leak. And so it'll sail right through leak testing. But if it had a leak, the silicones are not going to protect it once it's in vivo. So, and as I mentioned, the body's really pretty benign. Now, maybe a neurostimulator if you're tugging on the leads. So that's something to keep in mind. And then the question is, well, where should I set my hermeticity spec? Well, if you just default to the MEL specs, unless you want to comply with Class K space, I don't know that they're going to be good enough. You might want to consider something even tighter than an air leak rate of 1 times 10 to the minus 8. So, and then the other thing you need to understand, I'm going to talk about that in a minute, is how much moisture are you starting with? I mean, even though your glove box is bone dry and you got a dew-point hydrometer in there kind of measuring that doesn't mean once you put the lid on it, you're not going to have some amount of moisture that's just due to outgassing of the moisture that's absorbed. And then it's so the two go hand in hand. It's what are you starting with, and then what is the leak rate of the part.
So with that, there was a question from the audience on this. Is there data or research that shows moisture can be trapped they're saying in the plating of a hermetic substrate? So I'm assuming it's a substrate going in a hermetic container package, but it sounds like there could be moisture trapped in the plating, or they're asking if there
Sure.
can be.
Yeah, no, it's a good question. So the circuit board you build on inside the hermetic enclosure could be ceramic, it could be FR4 even, or something along those lines. But in the platings, you can trap moisture. Hydrogen is trapped in the platings. But any epoxy, that's really what sucks up the moisture. The epoxies you use for die attach, any kind of plastic parts, any kind of even coatings on capacitors, any kind of, if you're doing any kind of staking, there's a lot of moisture just gets tied up in general in any polymer. And even in room ambient, even in a relatively dry conditions, you can have quite a bit of moisture. So that's the reason for the pre-seal bake. Now this is very important to sufficiently dry out all the moisture that is absorbed either in the platings or in the polymers. And that could be 16 hours, it could be 32 hours. It could include a periodic flushing of the pre-seal vacuum bake oven. And then that has to be attached directly to the glove box where you're monitoring your 75-25 argon helium gas fill. So is there any research on that? There's tons of articles, talking about those issues. Honestly, I think any moisture trapped in platings is probably in the noise level compared to moisture sucked up in the epoxies. Okay, but does that answer it? Okay.
I think so.
Now, the other thing you got to be careful of, and this is a requirement in the mill community, we use RGA as a process monitor. So anybody that's on the QML, they call it, has to periodically take empty cans, like maybe once a month, and send them out for residual gas analysis just to check that 75-25 backfill you think you have. All right, and then you also need to put in some kind of inline, periodically pull a unit off the line and subject that to RGA. And you could have the best process going, but you change board suppliers and maybe you're getting a lot of outgassing you didn't expect. All right, so let's just briefly touch on RGA. I probably have a few more slides than I needed in here, but here's the other important thing is RGA or IGA, internal gas analysis, is generally considered a destructive test. You got to puncture a hole in it. So unlike, hermeticity data, you get a lot of it when you're in development. RGA data comes at a cost, but you can't beat it. I mean, it's really what you need to really validate your process and as part of in-process controls. Now in 1018, we precondition the parts. This is after you've created your hermetic seal. They still get soaked at 100 degrees C for 12 to 24 hours. And then they do the puncture and they test at 100 degrees C. Well, I'll get to it in a minute. You can't always do that with a medical device. But here's just a little more detail on 1018 as a trip. All right, and this is a typical RGA report. Now, moisture is the big worry, but there's other gases in here that tell a lot about your process. And just a couple of years ago, we spec out not only a moisture limit, but an oxygen limit and a limit on perfluorocarbons down at the 50 ppm level. But this actually was done to a commercial spec. So you got a battery in your pacer or in your device, you're gonna have to be careful at what temperature you do the RGA. And that's something that can be accommodated, but you're not necessarily in full compliance with the method, but that's kind of how people do it. So let's talk about the RGA spec. Let's forget about Hermeticity for a minute. Where are you going to set your RGA spec? In the MIL community, it's always been 5,000 ppm. And just put very simply, that puts the dew point below freezing. So as you're going up and down in temp cycling, and all the MIL products have that, when you're operating minus 55 to 125 C, you can be absolutely sure you won't have any moisture condensing out on the surface of your components. So that's one approach to the spec. Another one, which gets a little deep, is maybe look at surface area to volume ratio. Been a lot of work out there that says you only need 3 monolayers of water molecules to sustain conduction on the surface. So if you happen to have a part with maybe a real small volume and a high surface area, it's really like the high surface area to volume ratios. You could think of it along those lines and maybe alter your spec a little bit. But both of these approaches are extremely, I would say, conservative. I mean, we absolutely need them for the MIL community. But given a device only operates at a steady 37 C, maybe there's another RGA spec that could be justified, maybe something higher than 5,000. It's not out of the question, given you do your homework and you have the data. So this equation, I'm going to show you a couple of charts here in a minute. This equation describes how much water you'd expect to accumulate in a sealed enclosure, given a partial pressure on the ambient, and as a function of time and leak rate for the water going into the part and the volume. Okay, now in the body, the amount of water that's available at 37 C, the dew point at 37 C is 60,000 plus parts per million. And that's what really drives the reaction. It's in the molecular flow regime, it's the difference in the partial pressure of the gases that eventually comes to equilibrium. It's just a matter of how quickly, and that's a function of the leak rate. So if you know the leak rate for one part, you know it for everything else, according to gas flow theory, just the square root of the molecular weight. So let's say you had a part that you measured 1 × 10⁻⁸, and it had 25% helium in the backfill, and you calculated the air leak rate based on the true helium leak rate. It's a little confusing here. That would actually be a pretty tight leak rate. Okay, and then from that, you can move over to a leak rate of water vapor going into the part. And so that's what I'm showing you here. This is a part with a pretty tight leak rate, measured value 1 × 10⁻⁸. That's what the guy reads at the helium leak detector, with a presumed 25% helium backfill. Okay, no additional bombing, no more helium being pressurized into it. And if the package volume was 10 cubic centimeters, you would expect, and if you started with no moisture to begin with, it's only a couple of years and you're beyond the 5,000 mil spec. And then after 10 years, you're up into 25, between 20 and 30,000 parts per million inside the device. Okay. Now, if we go to a higher leak rate, if we change that leak rate just one order of magnitude, you can see in no time at all, I'm up close to that 60,000 point. And that's where you're going to saturate. You're not going to ever get more than 60,000 in there, because once the internal atmosphere comes to equilibrium with the body, I think it settles out about 60,000 parts per million. You can't get any more in there. So these kind of projections are important in development. To first of all establish what is my baseline RGA number I can expect right after seal, and then what is my leak rate in order to say you want a device to last 5 years or 10 years in vivo. Now, the other thing you got to concern yourself with is, sure, in the body, you never move off of 37 degrees Celsius, so you got other problems. But how about that 2 years before you implant the product? During that time period, you may see in transportation or in sterilization some elevated temperatures, which could increase outgassing of components inside. So with the same kind of modeling and that same equation, you can make estimates. Here's one, a part measured value in the nines, how much you would expect to accumulate inside the hermetic enclosure for a given leak rate, that leak rate. And you can see after 2 years in a tropical environment, you could be up to close to 1,500 ppm, ambient, dry conditions. So a lot of these products get shipped all over the world. So some of the challenges in the RGA test itself is that pre-bake out and test temperature. If you have a battery in there, you got to understand what that is. So maybe, maybe you dial that back and run some kind of a bake out less than the max operating temperature, and maybe test at 40 C instead of 37 to give yourself a little margin. RGA is destructive, and you really need some work up hand to verify you've got a good bake out, and you're not just worried about the expected lifetime, but the storage and shipping conditions prior to, any potential temp extremes in shipping, handling, and sterilization. All right, so where do we set that spec? Well, if you want to be conservative, if you want to complain, if you want to state to your customers and to the FDA you're in full compliance with 1018, 5,000 PM, 5,000 parts per million, I should have in there, parts per million, oops, is where you want to be. Now, I guess you have a battery, you're going to have to alter the test temperature. Or you could base it on the 3 monolayer theory. These two generally stand to be close to each other. Or maybe something higher than that, but still with plenty of margin, so you don't have any worries you're going to get anywhere close to 60,000 ppm, which means you basically have dew condensed out onto the part. And I probably mentioned this already. You really need to institute RGA as a process monitor and be pulling product off the line periodically, just because you can't beat good RGA data. Just bottom line, check that all your checks are working. All right, that's pretty much all I had to share with you. But this is a fascinating area. If you're a young engineer out there, I encourage you to get involved. There's a couple of great textbooks. One is Hermeticity of Electronic Packages by Hal Greenhouse. Actually, my colleague wrote one of the chapters in there, Bob Lowry. Guy Phil Schuessler, he actually uh, runs this conference. He's the head of it. I organize it. But we've all been kind of going to this for years and years. So there's a meeting or a conference up in the Adirondacks, and Phil's still active. He has a great book on volatiles and done a lot of work in hydrogen. And then in June, I'll have a couple of virtual classes, one on volatile control, which is hermeticity testing, RGA, and getters. I didn't mention getters, but if you don't think you're going to get there with your leak rates and whatever might be outgassing, then you could consider a getter to absorb the excess moisture. And then non-hermetics, that's another big area, which just a whole nother way of thinking. So hopefully that helps, and be happy to entertain any questions.
Thank you, Tom. Very, very interesting. So just to be clear, the outgassing test you can 100% test, but the RGA is destructive. So I assume you have to do a sampling plan. So the higher the quality level you need, you have to destroy more samples. So I mean, for a device that's going to go on a satellite, I mean, is it 50% sampling rate to, you know, or is some extreme sampling rate?
No, we kind of have our own system for satellites, and it includes inline group B testing. And what you're talking about is what we call group C. So we do periodically pull parts, and we deal with that all the time, very low volume. But it's just sample sizes of 3 or 5 that get burned in, temp cycled. Then we would do the RGA test, but then we also tear them down and do die shear, wire pull. So we extract a lot of information from those in-process, inline testing. But when I say it's destructive, it's really just you're poking a hole in the top. So you can still learn a whole lot about your process with some subsequent testing. And if you're able to solder that hole, well, I guess you wouldn't solder it back up, but yeah, to answer your question, it could be, I mean, you have other controls. Every device manufacturer is checking his glove box, and you're doing hermeticity testing. You got all your backup data. It's just an added part or two, not with any great statistical significance, but just an added check on actual product. That's what I would advocate.
Great. Let's see if there's some more questions from the audience. Did you want to show a video on, was that a
well, I had a little, let's see, I could show it to you. It's just basically a little video on bubble testing.
And so while Tom's getting that set up, if there are more questions from the audience, please put them in the Q&A tool.
Okay, here's a part. This is a microwave component. This gold embrittlement. You can
You're
see
still sharing your slides, so you need to either share your whole screen or
share. Oh, I just got my slides up there.
yeah.
Oh, okay, let me try this. You see it there?
Not yet. Maybe share your whole desktop or share your.
Let's see here. Screen share. You can see my, you don't see this little video?
No. Here, let me take the
That's,
screen share back, and then there we go. Now we have it. Okay, go ahead.
Okay. Yeah. So this is the bubble test. Right here, you can see a leaker. So that's why I like, I mean, a lot of times there's a lot more feed-throughs, but as a microwave feed-through, and it was gold embrittlement, cracked it. And you could see just by that, that's on top of the port for the leak detector. We're dabbing some IPA, and you can see the bubbles indicating exactly where the leak path is. But these leak paths we're talking about for fine leaks, I mean, they are just microscopic leak paths, and even high humidity is enough to temporarily plug them. And it's just now, the last 3, 4, 5 years, the community's getting used to making measurements down in the -11, -12 range. So for years and years, most leak detectors, the sensitivity, even now, if you just have an older style Vico leak detector, in a production environment, you can't get your backgrounds really much below 10 to the -9, maybe high 10s. And now the leak specs, if you have an air leak rate of 1 to the -8, well, depending on your bombing conditions, you're going to have to make measurements in the 10s and maybe even the 11s. So, but there's equipment out there for that. And if you really want to be absolutely sure in a medical implant that you've got sufficient protection against moisture, then you might want to consider some of these tighter specs and really get a handle on the outgassing and the RGA, and then you can sleep good at night.
Well, I thank you very much, Tom. It looks like our audience is either still processing or absorbing, so there are no other questions at this point, but I want to thank you very much for an excellent presentation. Just like to wrap up, remind you that we have a speaker series presentation scheduled for April 7th and April 21st. We will, as soon as the presenters are confirmed, we will send out email, let people know. And then please take a look at our supply chain security event. It's a free online event, April 28th and 29th. You can sign up at meptec.org. We look forward to a very active discussion there as the challenges to securing the supply chain in the era of advanced packaging. And with that, I will wish everybody a good rest of their day. And thank you again, Tom, and look forward to seeing everybody at a future event. Thank you.